simulation, one of the main roles for it is to give you an insight, a microscope into what's happening in these systems at the molecular and supramolecular levels. And that, I think that will really help formulators understand their systems better, focus their formulation testing better, and perhaps get better outcomes. Modeling is in the light blue here. So we can generate variations on those ideas, and we can test those and rank those variations computationally. And in the end, we allow the formulator to focus in on a set of the most promising variations to test and assess. And then you still may iterate, but the expectation is you will be making fewer formulations and you'll be doing fewer loops around this cycle. And so this should save time, it should save money. And I also believe that it will generate information and knowledge along the way that will help with not only this project, but future projects. Why do this? And I've mentioned that lipid nanoparticle structure is poorly characterized. Now, that's true in that if you have a solution with lipid nanoparticles in it, it's pretty easy to experimentally detect those lipid nanoparticles and to characterize their size. It is really hard to characterize if there's any structure inside them and what that structure is. There have been a few experimental studies. These are massive studies using atypical analytical equipment. They're huge contributions to science, but they're not something that you can do routinely in industry. This is very effective at creating a coarse-grained model. And we've employed this for the studies in this presentation. So creating a coarse-grained model for lipid nanoparticle vaccine development is practical. And you can see there's a lot of this light blue, that's water, inside the lipid nanoparticle. In fact, it's about 25% of what is inside the lipid nanoparticle is water. And this is consistent with published information from scattering experiments where they've carefully analyzed them. Admittedly, those are for different formulations, so the correspondence needs to be taken with some caution, but it's encouraging that we're getting a similar high level of water present. The other thing we can do is now we can imitate another part of this finishing process, and that's where we're raising the pH from a relatively low pH, 4 or 5, used for encapsulation, up to blood pH 7.4. As you can see, as you're getting less and less ionizable, positively charged ionizable lipid, the RNA starts to separate out at about 50%. And this is the Pfizer-BioNTech formulation. And then we can also characterize composition of the interior versus the shell of the lipid nanoparticle. There's some experimental information available on that. Many companies are trying to discover new ionizable lipids, and we believe that the ability to predict the apparent pKa values will help in this process, because it's not only just the molecule itself, it's how it behaves in a more complicated formulation, and we can calculate that. From the difference in these curves through this equation here, we're able to calculate a shift in pKa due to this change in environment, and we add that to the intrinsic pKa that we can calculate using quite a few programs, and that gives us the apparent pKa of the ionizable lipid. And so we've done this for 4 different formulations. The first one is the Pfizer-BioNTech vaccine. Spikevax is the vaccine from Moderna. Onpattro is that previously marketed siRNA vaccine. It has all 3 have different ionizable lipids and slightly different formulations. Now, for validation, if we just did these 3, that would be a tough validation, because they're all going to have pK values about the same. And so we don't know if our method gave the same answer. Is it just that it's always giving that answer regardless of that? So we asked our collaborator, Steve Arns from Acuitas, they're the company that makes the lipids for Pfizer-BioNTech vaccine, for an alternative lipid that has a very different apparent pK value, and that's just lipid A. And then we did our calculations.